5 minutes, but at the most 10 minutes. The quizzes in total are just going to be worth 25 points. This is on page 2, the course information. And so this quiz is just going to be worth 1 point, so like a half a point per question. Altogether, we're going to have around 875 points in total. So it's not worth that much. But we'll have a number of these, some worth more than others. Total 25. Where most of the points are wrapped up are going to be in the midterm exams. These midterm exams, we have 4 of those with 100 points each. So it's going to give us 400 points. It's about half your grade right there in the midterm exam. And the final exam is also worth a significant chunk of your grade. The final exam is going to be 175 points, which works out to like 20% of your grade. And so altogether, the exams are where most of the points are wrapped up. In lab, if you look at the labs and reports, we're going to have a total of 9. I'm dropping 1 lab, so I guess we have a total of 10. I didn't count correct. It's going to be 20 points each, 180 points. So again, about 20% of your grade. And so mostly exams, and then lab would be the next biggest chunk. Quizzes are minor, and then this lab technique. Lab technique is just safety, preparation, efficiency, cleanup, just general technique score. So it depends on the course percentage. Like a point on the quiz is the same value as a point on the test. They aren't weighted differently. And so if you have 90% of the points or above, you're going to be guaranteed an A. 80% for a B, and the cutoff for a C is 65%. Sometimes the percentages will drop a little bit depending on how hard I write the test. So, 90 to 88%. But for sure, if you have 90 and above, the 65 cutoff doesn't change. Normally, a lot of people will assign 70% for a C, a wide C window. Okay. Now, the lab is not worth that many points, but there's a problem with articulation to schools. Articulation just means we have an agreement with, let's say, UCLA. At UCLA, they separate the lecture from the lab. The lecture is worth 3 units at UCLA, the lab's worth 1 unit. I mean, 2 separate courses. And so you could fail lab and just fail lab and still pass lecture. Here, we combine it into one course, one 5-unit course. And so, because of our agreement with the universities, we have to assure them that if you fail lab, they want you to repeat the course. Actually, they want you to repeat the lab. If you fail lab at UCLA, you retake the lab. Just try it again. But here, if you fail lab, you can still pass the course. Well, they don't want that. And so, I'm aware that a lot of people will look at the points and say, I don't have to attend lab today. I have plenty of points. Depends on what your goal in the class is. So they'll skip lab. But you can't do that because of our articulation agreement. I'd have to fail you if you miss a lot of labs or a number of labs. And so there's only a certain, I'm going to have a makeup. Things happen, and you might miss a lab, but we'll try to make it up. Sometimes it's doable, sometimes it's not, depending on the setup. Because the labs are used by multiple sections. Not only that, different classes too. So they have to pull out all the chemicals and then put in a different lab for the other class, which is like Chem 20, which uses lab, I think. Some others. And so we'll look at that lab by lab. But make sure that you come to lab. Lab attendance is mandatory. Even though it doesn't seem like a huge chunk of your grade percentage, it's weighted abnormally large. It could actually force you to fail the class, even though you might be getting A's in the exam. So keep that in mind here. Well, we have some course objectives. You could read through these. Basically, this course is supposed to be equivalent to the courses offered at UCs and CSUs. Actually, is it offered? I think they have intro chem there, but it's equivalent to 1 year of high school chemistry, compressed into a semester with that. We have certain student learning outcomes. There are a whole bunch of learning outcomes that were presented in the chapter. These are two, but two of many. We talked about the required materials yesterday. The required assignments, there are going to be no dropped exams. The labs, I'll probably drop your lowest lab score. I think, yeah. Here, your lowest 20-point lab will be dropped. Makeup exams, depending on the circumstances, could incur a penalty. But I take those case by case. The standard penalty on a makeup exam is 10%. But you might not get penalized. So we're looking at those. Okay, excessive absences will result. Excessive absences in lab will result in being dropped. To save time, well, lecture is important to attend. I would never miss personally, but if you do miss lecture, you're not going to lose any points for that. But if you do miss lab, you will lose points for that. Okay. If there are any, special needs or requirements that you have, let me know on that survey I just passed out. We'll try to make accommodations for any requests that you have. And you can leave any comment information there as well. There's also a special resource center too. Some people like to take the test there. Okay, if there are any changes to the schedule, I usually make an in-class announcement for this. I'll try to post it on Piazza as well. Okay, a note on cheating. Any evidence of cheating will result in a report to the dean. And for academic honesty is mandatory. Okay, getting help here. If you need help, like a question, you might just write it on Piazza, and I check those. If you see the question pop up, go ahead and answer it if you know the answer. Because sometimes it takes me some time to get to it. Free tutoring is available in the library. They haven't posted the hours yet. They have Chem 4 tutors there. The MESA program, if you qualify for MESA, then they have free facilitator-led study groups with no financial or time commitment. So it's a pretty good deal. You can try this Khan Academy or the study.com. There are a whole bunch of additional resources there, video lectures, and other textbooks. Are you guys familiar with the study room? Okay, when you walk into the corridor here, on the first door on the left is the student study room. And there's a small library there of texts you come through. There's some tables set up there, so you could study there. It's usually pretty quiet. A good place to study before or after class. All right, any questions on this? All right, we looked at the syllabus, so this is just arranged by chapters. Chapter is going in order, and the exams are pretty well spread out. I don't have the quizzes in here, though. Just be aware of that. All right, the other thing I was going to ask you is regarding office hours. You know, that's another place where you can seek additional help during my office hours. Usually I schedule office hours like before class or after class. I was thinking I'll schedule it right after class, like 20 or 30 minutes after class. And then before my afternoon class, which starts at 2. But if you have some specific time requests, write those down on the survey. And I'll take a look at those. And then I haven't finalized my office hours yet. I'll do that probably tomorrow. I'll announce my office hours. You can always catch me like right before, right after class. It's a good time. You can also call me here. And then it's kind of, there's people trying to add the class. So if you're going to be absent, you know, this first week, just shoot me an email or leave me a voicemail letting me know that, you know, you're still planning to attend. You just were absent for a particular day. And that way I know that to save your spot. Did I have one late? I already called roll. One late, two late. What are your names?
George.
George. Last name? George, are you on the wait list? Okay. Oh, I gave you the ad yesterday, right?
Yeah.
And then Carlos Hernandez. Oh, okay. All right, are you guys done with the quiz?
Yes. The dates on the list are off. The first starts with August 12th.
All right. Yeah.
Is it just the first 2 weeks? Or?
No, you know what? I screwed this one. I had changed the dates, and then I didn't save it, and then my computer updated and restarted, and then I thought I'd fixed it, but I didn't. Okay. You know what? I'm gonna give you another one. Let me fix this. I'll fix that. I'll fix the typo there too. But the dates, yeah. Shoot. This will be the third time.
What are you talking about? Today's totally August 13th.
Okay. All right. Yeah, wow. So yeah, when I uploaded these online, I didn't realize that. Shoot. All right, thanks for letting me know. But I'll fix those. That means the ones on Piazza are the same. Are the ones on Piazza the same?
I think it's the same.
It's all screwed up. All right, I'll fix those ones on Piazza as well. But the weeks are going to be the same, so we're still in the first week. And still on chapter 2 here. If you guys who came in late want to do the quiz, you could do it right here. Just do it quickly. All right, so do you know the difference between macroscopic, microscopic, and particulate?
Yes.
So can I collect those? I'm just pass them down. Okay, any others? So, like a chart like this, oftentimes what I'll do with a chart like this is I'll look at the range. You know, it's like if you're looking at some forest, you know, and you know, one of the things you could do in a forest is figure out, you know, what's the smallest, you know, the smallest tree maybe, and the biggest tree. And so we see the range of things. So if you look at the smallest, about how big is the smallest thing on this? About how big is it? Well, it looks like about 30 picometers, but around 30. P stands for pico.
Oh, I thought it was all the way where the line is.
Oh, here? Well, there.
No. Because see where it says atom and then there's a line going down to the little bar?
Yeah, this would be 10 picometers, so they're just estimating. If this is 10, you know, this is 100 picometers, so it's around here, let's say. You would say it's, so actually, it's around tens of picometers. Not really tens, it's not really even 30s. It's more like, if you're looking at the diameter of this, the diameter of this is about 100 picometers. What do you think the, you know, atoms, are all the atoms the same size? You know, no, some atoms are smaller, some atoms are bigger. Do you know what the smallest atom is? You would think it's hydrogen. You know, I would assume it's hydrogen. That's what the periodic table starts with. Are you guys? Has anybody not taken like physical science or that or chem before? Okay, so since high school, but you remember from high school hydrogen? No.
Well,
Okay.
a little bit. Not very much. That was a long time.
That was a long time. Yeah, normally we think hydrogen because hydrogen, you know, starts there and gets bigger, but it turns out it's not hydrogen. It's actually helium is the smallest. But a hydrogen atom is about 100 picometers in diameter. So 100 picometers, which puts it around here. But it's hard, you know, hard to say, you know, how you define the diameter because atoms are kind of funny, and we're going to talk about this later. But it depends on what, you know, if this is not a hard shell around the atom. And so if this atom is attracted to an oxygen atom here, it can be pulled in closer. You know, what they say is the surface of an atom is like a rotten grapefruit. In fact, that comes from our book, a rotten grapefruit. And so when you're trying to probe it with something hard like this, okay, where's the surface of the atom? You know, it's not like this. It's like, you know, it depends on how much force you put on the probe, right? And so the atom is like a cloud. And so when we define the radius, then we just have to put in the probe with the same force, you know, and then that's how we measure it. Or we measure it, you know, if it's connected to something. This is water molecule. Water molecule consists of 2 hydrogen atoms and 1 oxygen atom, so this one looks bigger than 100 picometers. And so atoms will range from, like, say 100 picometers to, you know, 600, 700 picometers diameter. And so picometers is a common unit that we recognize because why do I remember picometers? Why I remember picometers is because that's about the size of an atom, you know, on the order of 100 picometers. Actually, there's a unit that was, for me, was even easier to remember. You know, how big is an atom? How big is an atom? I used to use these. Does anybody recognize this symbol? This symbol, this is called an angstrom. And an angstrom is defined as 1 times 10 to the minus 10 meters. 1 times 10 to the minus 10 meters, we're going to get into this in the next chapter. 1 times 10 to the minus 10 meters is equivalent to how many picometers? Well, it's equivalent to 100 picometers. So that's the same as 100 picometers. And so when I think of atoms ranging in diameter from 1 to 6 angstroms in diameter, or 100 to 600 picometers in diameter. And so that's for us the small end of the scale, because do we work with things that are smaller than atoms? Are there things that are smaller than atoms? And this is the realm of particle physicists. There are. Those are called subatomic particles. But what happens? Now, an atom is the smallest piece of matter that retains the properties. If I try to make it smaller than an atom, which is possible, like say I take a copper atom. The copper atom is kind of big. If I take a single copper atom like this and then try to cut it in half, would I get half a copper atom? No. If I take a copper atom and then try to break it into smaller pieces, I'm going to get not copper. I'm going to get things called protons, neutrons, and electrons. Protons, neutrons, and electrons, you can't say a proton behaves like copper. A proton is not anything nowhere near what copper is. And so what happens is, like, did I talk about the copper yesterday? I didn't talk about the copper? Okay. Yeah, I talked about it in the afternoon class. A question came up in the afternoon class. The question was this, about theories. What is at the top? A law or a theory? If you want to understand, nature, then you want to understand the laws of nature, right? And therefore, the laws of nature are more descriptive, more informative than the theory of nature. Would you agree? And so people want to understand the laws of nature. But it turns out it's the opposite. The laws, at least, it depends on how you define it, because normally we watch documentaries on the laws of nature and that type of stuff, but really what they're talking about are the laws that come from theory. Laws can come from empirical, and laws can come from theory, so they're in that case. And so even though they're talking about the laws of nature, they're looking at it coming probably from both from, what did they say? Both from, what was one side of the theory, or observation. Observation, the problem with observation is you have to observe everything, right? Unless you see a pattern. So for example, like I said the other day, if you want to understand Doberman pinschers, are you going to have to observe every single Doberman pinscher alive in the world today? That's typically, when people think of observation, that's typically what people think, because they want to know what the outliers are, and what the general trend is. How far is that spread? This is what people want to know, the extremes. How far are the extremes out there? Well, if we have a good understanding of theory, then we could easily derive the laws, right? Because the theory is just what? The theory is a fundamental description of the laws, and so it should be easy. And so it turns out that the theory is theory. Not only we have theories like that, but theory should be able to predict new laws. And so one of the new laws that a theory predicted, and I gave an example of this the other day, was this. There were two competing theories about matter. One theory of matter was like this. Macroscopic, you look at copper, you look at a piece of copper in a penny, no problem, right? And then you keep breaking that copper down smaller and smaller. Pretty soon you're going to need in order to see this tiny pieces of copper, you're going to need a microscope, right? And then you keep breaking it smaller and smaller, and pretty soon the microscope can't even detect it. You're going to need what? You're going to need something more sophisticated, like a electron microscope or a scanning scanning tunneling microscope. Something like that to detect it. And then we keep breaking it into smaller and smaller pieces. Now the two theories were this. One theory is that you can break it down infinitely small. There's no limit. You just break it smaller and smaller and smaller and smaller. How small you break it just depends. And so that was one theory. The other theory regarding matter is this. You know, the smallest piece of matter that you can have is an atom, which is like this spherical object here. Because if you try to break the atom into smaller pieces, it's no longer going to be copper. And so the smallest piece of copper we can have is an atom. And so those are two competing theories of matter. And so which one would you agree with? And why? This is part of the scientific method too. Part of the scientific method is this. When I was in junior high school, I learned about atoms, and I just accepted it. You know, the science teacher told me about atoms. I accept it. I believe in atoms, right? But what happens is, well, that's in junior high and high school, whatever. But when you get into, you know, the colleges, universities, somebody's going to say, "Why do you believe in atoms? What makes you okay?" I'm skeptical. I think that matter is infinitely divisible. So you give me your evidence that atoms exist. And so what would you tell them? This is let's say your friend. Your friend doesn't believe in atoms. What would you tell them? Okay, so what kind of evidence? Well, you have to think, when were these theories proposed? Do you know these theories were proposed in the 1800s? In the 1800s, did they have scanning tunneling microscopes? No. In the 1800s, how did the guy who came up with the first theory for atoms is named Dalton? How did Dalton convince all the skeptics to believe in atoms? Based on some, experimental results, or based on some theory? Well, the theory is atoms, right? And so how do you prove that theory? Well, the theory came from where? The theory wasn't just popped into his mind one day. You know, he's walking down the path, and all of a sudden he thinks, you know, the theory pops in his mind. Well, maybe it did. I don't know, but normally theories come from what? So there must have been some experimental evidence that suggested the existence of atoms. What was that experimental evidence that suggested the existence of atoms? This was the experimental evidence that suggested that atoms exist. You know, matter contains mass, correct? And so what happens is, if you weigh this, you know, air has mass. If you weigh this before, like, you can tell if a tank is empty or if a tank is full. Like, have you used those compressed air things to blow off dust? You know, it's heavier at the beginning when you start using it, but when it's dead, it's pretty light. It's not filled with as much air. Well, all this air weighs something here, and actually we can weigh it on a balance. And the same thing over here, you know, it weighs, and you think this weighs less because there's less air, but do you know what the weight is over here versus here? The exact same. These two things weigh exactly the same amount. And so, you know, this pattern, this is an observation. This pattern repeats. So for example, if you burn mercury, the same exact thing happened. The mass before burning and the mass after burning are exactly the same. Well, I shouldn't say exactly, but as far as they could tell, it was exactly the same. And then they burned other things. You burn wood and you capture the gases that are produced. You capture the gases that are produced and weigh it. And so you weigh the wood before, it's heavy, right? And you weigh the ash after, the ash is light, but when you weigh all the gases that are produced, like for example, do you know if you burn 1 pound of methane, if you burn 1 pound of methane, I did this calculation a while ago, and my memory's bad, but I think you form 4 pounds of water for every 1 pound of methane that's burned. Can you believe that? Well, you can weigh it. See? And how many pounds of CO2? I did that calculation. We're going to do that calculation. I did that calculation at the beginning of last Chem 4. Well, anyway, and so if this is a repeating pattern, then we can call it what? We can call it a theory. No, we wouldn't call it a theory. We would call it a
Generalization.
Well, generalization has lots of exceptions. You know, when you make a generalization, I'll make a generalization of the students in this room, it's going to have a lot of exceptions, right? I want to make a generalization because this is much more concise. The thing is, you guys, like after yesterday, what you should do is, okay, well, you know, every day you have some kind of learning objective, right? And so sometimes it takes time to get it to sink in. And so you want to know something that I did as a student? I changed the way I studied dramatically, because when I was at Santa Barbara City College, I had my system. You know, I did the book, I highlighted the book, I annotated the book, I did that. When I got to UCLA, I did the same thing. I studied the exact same way, but it was not successful, you know, because I struggled the first quarter. You know, they said, oh yeah, when your first quarter here, your GPA is going to drop by 1. And actually it happened. When I started at UCLA, my first quarter there, my GPA dropped by 1 unit. Oh, I don't want that, you know. And so then the next quarter I thought, okay, I'll just spend more time, but the problem is it was my first quarter there and I was warned beforehand. And so all I did was I studied, that's it. I didn't do, well, I also worked in the cafeteria, but that was my first quarter. Worked in the cafeteria, and then a finals week came, and then 5 people quit the cafeteria and everybody got assigned extra shifts, so that wasn't good. So I ended up, but I stayed there till the end, but I had to change. So the next quarter I spent even more time, but you know, it wasn't successful initially, and then I thought, I'm not studying right, I got to study differently. And so I was sitting next to this other guy who got the top score. This is physical chemistry I was taking, which is a blend of physics and chemistry. And so I started talking to him about how he studied and all this. And I got some useful tips that I incorporated into how I studied. And so one of the things that I did, and this didn't come from him, he gave me other tips, but one of the things that I found very useful was this: I don't have that great of a memory. And so what I do is, I take my notes and then I review the notes. I review the notes regularly. And so let's say yesterday we learned about the scientific method. By the time the midterm comes, I would have read that scientific method many, many times over, because whenever I had some time, I just flipped through my notes from the first page on. Well, how many pages of notes do you have now? A couple? So it doesn't take much time to review that, right? And that repetition will help you, get it into your subconscious. You know, because then once it's there in that the longer term memory, then your brain can start building connections, you know, subconsciously. I started reading books on studying too, because the struggle I had at the beginning. But finally, I hit something that worked. And then after that, then it was back to normal. Because when I transferred, yeah. Well, anyway. So what you need to do is you need to go back through and reread. Like you could reread your notes before class. You know, there's some dead time there. Just flip back. There's only 2 pages, 3 pages, 4 pages of notes. Just flip back. That way, you know, when we're in class here, it'll be easier to recall. You know, it'll be easier to recall things like this. Well, anyway. So if we see a regular recurring pattern like this, then we'd like to devise a law, right? A law. And the law for this is called the law of conservation of mass. That is, the mass before is the same as the mass after. That is, there was no change in mass. And so the law of conservation of mass is when we have a chemical, you know, this is what we call a chemical change or chemical property, burning, you know, combustion or burning in air. Then, you know, that's what, actually, did I get all the quizzes done? So, you know, that's why, and everybody will have their own words. It's best if you can put things in your own words, but I'll talk about this law of conservation of mass in just a moment. But, you know, what to me, what scientists do is they just try to understand, you know, understand nature. What chemists do is they try to understand matter. They try to understand the matter based on its composition, right, structure, in order to figure out the properties. So chemists are most interested in the properties of matter. You know, how matter behaves. You know, is the matter stable or is the matter unstable? You know, some matter out there is quite vicious in its instability. You know, it likes to attack things. Like chlorine, you know, pools that are over-chlorinated, all that chlorine will start burning your eyes, right, your skin, etc. But yeah, so but you want to put it in your own words because, you know, and this is the other thing I did. You know, I just didn't write the notes verbatim. What I do is I'd write the notes and then write like a little take-home message. The take-home message was in my words, you know, things that I would understand that I would remember. So I try to do it that way, rather than memorizing. Okay, he said this, he said that. You know, so try to do that. Well, anyway, this led to the conservation of mass, which is a law. And so, why would mass be conserved? Well, that means you know, all the matter that was in there before is still there, but it's different now. You know, like for example, when you burn methane, the methane's no longer there. And so this is where atoms came up. Atoms came up was that if we have methane, then we got atoms in methane that are going to be rearranged to form. You know, when you burn methane in air, do you know what you form? Water and carbon dioxide. And so the atoms in methane and oxygen get rearranged to form water and carbon dioxide. So this was the basis of this theory. But then, you know, the people who are still talking about infinitely divisible, what sealed Dalton's atomic theory was this: theories should be a fundamental description of what's happening. So what's happening? We got these atoms that are being rearranged in this chemical reaction, which we call combustion. But theories should do one more thing. You know, theories should do what? Predict. And so what the theory predicted was this. The theory predicted a new law. Dalton's atomic theory predicted the new law. It's called the law of constant composition, or the law of multiple proportions. That is, when you have water, it's always H2O. But why isn't it like H2.10? Why can't we have H2.10 or H1.950? Why can't we have that? You know, so if matter were infinitely divisible, it would make sense. You know, I could have any amount of hydrogen I want attached to the oxygen. So let's say, hey, you know, I'm on a low hydrogen diet. I just want my water with a little bit less hydrogen. Can you make it like a H1.90? Is that possible? Oh, well, you know, you could have more hydrogen. You know, I'm on a high hydrogen diet. So you probably heard this joke. Have you heard this joke? Two people walk up to the bartender, and one person says, I'll have an H2O. And then the person's friend says, I'll have an H2O too. Do you get? And so H2O2 is not water. H2O2 is, you know what H2O2 is? It's kind of like water. But this is called hydrogen peroxide. Hydrogen peroxide, unfortunately, is pretty deadly stuff. And so the joke is that the person who ordered the H2O2 died, you know, from consuming the H2O2. Whereas their friend survived just drinking the H2O. But you know, why isn't it H1.5O2? You know, and the reason is because things come in discrete balls like that, and those are the atoms. And so we can't have we can't have a half an atom. Can we have a half an atom? No. And so this is okay, and we're going to see this throughout, you know, our studies. It's either CO, which we don't want CO, because we would rather have, if we're going to have CO, we'd rather have CO2. And so CO, this happens all the time. You know, people have what we call poorly tuned burners. You know, not enough air is getting in there, generating too much carbon monoxide. This is why a lot of houses have carbon monoxide detectors, because if your range burners or your water heater isn't operating at good efficiency, you're going to be generating a lot of CO. But hey, wait a minute. You know, if I just make it a little bit more efficient, won't I get some CO 1.5 or CO 1.2 or CO 1.1? No, it's either going to be CO or it's going to be CO2, but nothing in between. And so this is what Dalton used to convince people of his theory, atomic theory. He didn't have these fancy instruments that we have nowadays. Nowadays, you know, IBM comes up and they manipulate single atoms on a plate, you know, and they can push these atoms around with a tiny probe, you know, and arrange it. Have you seen the Xenon Man? Or, these are the Xenon Man is well, I don't know the gender wise, but I think they called it the Xenon.
That's a nice atom.
Maybe I should spell out xenon. Xenon. There we go. These are creations by IBM, as you can probably tell. These are single atoms here that they arranged to spell out IBM. Those are xenon atoms. Xenon atoms are kind of big. Bigger side. This is supposedly the Xenon Man here. But still pretty cool that, you know, if somebody doesn't believe in atoms nowadays, then they're one of the, you know, the outliers, you know, extreme outlier, because everybody believes in atoms because people have manipulated single atoms. You can visualize single atoms using X-rays, scanning tunneling microscopes and whatnot. Have you heard of atom smashers? Atom smashers. Atom smashers are things that can accelerate these atoms to very high speed and try to break them into small. And they do. They can break atoms into smaller pieces, but when they break atoms into smaller pieces, they don't get atoms, little atoms. You know, they get subatomic particles. Those subatomic particles are the realm of particle physicists. So there's a big atom smasher. They call it the Large Hadron Collider. Have you heard of that in Switzerland? Yeah. It generates huge collisions, huge energies. So they're expecting some pretty grand results from it. But there is some interesting theory and interesting experiments coming out of there. Okay. Well, anyway, so we're already using a combined approach of observation and theory. And although we really haven't talked about much of the theory of matter is matter consists of atoms. Atoms are the smallest piece of matter you can have. However, it depends. Water. You know, the smallest piece of water I can have, would that be an atom of water?
No.
We don't call it an atom of water. When we have two or more atoms put together, and they're held together in such a way that we call it bonded or chemically bonded together, then this is the smallest piece of water we can have. And we don't call this an atom, we call it a molecule. And so copper doesn't form molecules. Copper, the smallest piece of copper we can have is a single atom of copper. The smallest piece of water we can have is a molecule of water. What about the smallest piece of gold? If I was looking at the smallest piece of gold, gold is AU, as a symbol, it would be an atom. And so we take it case by case and we look at it there. But water would be a molecule. Now what we can do is we can break this up into atoms. And so if we put this into like an atom smasher type device, we can break it up into atoms of hydrogen and atoms of oxygen, and then go from there. So molecules can be broken up into atoms. Those atoms can't be broken down further without losing their identity. But water would lose its identity once we break this apart. The same thing here. This is a bigger molecule. This is aspirin. Here we can see it consists of carbon, hydrogen, and oxygen. This is a big molecule, although it's shrunk down in scale. This molecule is massive. It consists of hundreds, 500 atoms. Viruses are going to have a whole bunch of different molecules and other things together. Structure. All right, so we look at here, macroscopic, we have different scales, but on the small end of the scale, we're looking at what? You remember on the small end of the scale, we're looking at 100 picometers or 1 angstrom. When we're looking at that, a lot of this comes from experimental data. Did I talk about water? How do they figure out the structure of water? How do they figure out the composition of water?
By freezing it?
Did I talk about it already? Yeah, freezing it and taking the X-ray crystal structure. So I showed you some experimental data for that. But you know, sometimes it's hard to see from those X-ray crystal structures. So what we use models to represent it. And we have different ways we model these molecules or what we call it when 2 or more elements are combined, or 2 more atoms combined, we can form compounds. We have ball and stick, space filling, etc. A whole bunch more. But you can kind of, it's pretty obvious when you see it. This is ball and stick. You know, it's got a bunch of balls representing the atoms of sticks. There are no sticks in real life. the reason they have the sticks here is just to separate it out. So the carbon atom. This is methane, by the way. So the carbon atom in the center is more visible. Then you can see the geometry of this. The geometry, that is the shape of these molecules, is very important. Do you know what this shape is called? This shape is given a name. It's called tetrahedral. It's a very common one. Here's a ball and stick model. Here's a space filling model. Again, atoms are not, if I were to hit the side of that hydrogen, it's not like this. It's like a soft probe. But they have to pick a border. And so this border they outline here to give you a general size of the molecule. So it's taking that probe and probing it. And so this is visualizing both on top of each other. Now, the carbon atoms aren't literally black and hydrogens aren't white. It's just so we can easily see that here. They're kind of the same color, white on white, so they shade them. This is the smallest piece of methane you can have, and that would be a molecule of methane. I think most people are familiar with H2O. H is the symbol for hydrogen. O is the symbol for oxygen. So this just shows we have 2 hydrogens for every oxygen. And so when we think about this, this would be a molecule. We have 2 atoms of hydrogen for every atom of oxygen. Do you know that there are many different types of atoms? Hydrogen and oxygen are 2, but we have lots of different types of atoms, and these atoms are different sizes. I told you which one was. Do you know what the smallest atom on the periodic table is? Helium. Helium is the smallest. Do you know what the biggest atom on the periodic table is? Actually, maybe I should put the periodic table up on the board here so you can see it. There are lots of good online periodic tables, ones that you click and you can see a lot of the see if this is it. No. Some of these you can click and then it'll show you a whole bunch of stuff about it. Helium is the biggest. The symbol for helium is He. And so let's say a hydrogen's this big, small, helium would be like this big. But what would be the biggest atom? If you were to just take a random guess. Uh-huh.
I can't see what it's called, but number 118
Okay, this one? Yeah, well actually this one, unknown. Well, some of these represent the number 118. Others are named after people.
Like Laurentian.
Yeah, Laurentian, European would be a country. Berkeleyan would be a school. Californian would be a state. Anyway, getting back to this, yeah, you're right. This is a lot bigger, but it's not the biggest. Yeah, it would be on the left-hand side. It would be. This one's named after France. This would be France. Francium, it's the biggest, but francium also turns out to be an unstable atom. There are atoms that are stable and there are unstable atoms. These unstable atoms are radioactive. And these unstable atoms can actually break apart into smaller atoms because of their radioactivity. But chemists, there are two really main types of chemists. All the chemists that I showed you, the analytical chemists, the whatever chemists, those are chemists that are interested in chemical properties. And then you have nuclear chemists. Nuclear chemists are interested in what we call nuclear properties. And so nuclear chemists look at different things than chemical chemists. And so francium, we look at the chemical properties of that, it's fine, but there's one more property that's radioactive. As are a lot of these other, like uranium, neptunium, plutonium, all radioactive. These are unstable atoms. So these atoms actually do break apart into smaller atoms, but not smaller uranium atoms, other atoms, which are called daughter. But this would be the biggest. But the biggest stable one would be like cesium. Cesium's stable. Cesium's well. All right, let's stop. We're going to take a break for 10 minutes. So, and then we'll start again.